My name is Gabriel Gafford, and I teach at Benton High School in Benton, Louisiana, located in Bossier Parish. One of the things that I'm passionate about as a teacher is making sure that my students have a really well-rounded education in science. That doesn't mean I want them to be geniuses in physics or biology or chemistry, but that does mean I want them to be able to apply some of the things they've learned in their everyday lives, even if that is a little minute thing that they have. The content that my students will be learning today will include the idea of precipitation reactions, which is the fancy name for double replacement reactions, and it's one of the 5 ones that they've already learned. The content that I'm using for all of my general chemistry students comes from the College Board. I'm using the pre-AP framework, and I'm also using AP chemistry materials for that. One of the things I like about the College Board is that it's really accessible for all my students, and I'm thankful that Bossier Parish has that. I have 2 goals for today's lesson. 1, that students will be able to draw particulate diagrams for double replacement reactions, and 2, that students will be able to predict the products of double replacement reactions using solubility rules. Prior to this lesson, I spent a little bit of time working on how to balance chemical equations and how to predict products of several different types. This is a useful skill because students will need to know how to apply this in different situations in chemistry. And as far as balancing chemical equations, they're going to need that for today's lesson on net ionic equations. Before the lesson, I also spent a little bit of time working with different teachers at the school, consulting with AP Chemistry teachers on Facebook, and looking through the College Board material to see exactly how the best way I can teach this lesson. As far as how this connects to my overall goals, students will be able to take this information with them to higher science level classes and apply them in different situations. This is important because we want our science classes to be interconnected and, most importantly, vertically aligned. Some adaptations that I made for today's lesson include setting up students with others that I know will be very beneficial to them. Welcome. All right, so today's different. We're not gonna actually take our green sheets out. The bell ringer today is gonna be a discussion. So what I want us to do real quick is look at this. At this point in your learning, how would you define a chemical reaction? We have done so much with balancing equations. So I want you to get with your shoulder partner, so you two, you know the deal, and discuss this. Take about 1 minute, then after that, we're gonna talk about it, all right?
I guess maybe
the reactions, yeah.
thinking to a product.
So let me have that back group. What would you guys say? How would you define a chemical reaction?
Well, we said that it's a reaction that creates a new product.
Okay, that is definitely true. Chemical reaction is something that produces something new. What would you guys say? Actually, right here, Parker, what do you guys say?
We said when 2 elements or several elements undergo a change that alters their chemical state, or
Ooh, I like that. Alters their chemical state. Can you give me an example of a chemical reaction?
Iron rusts or metal rusts, and then iron acids.
I like that. So iron plus oxygen makes iron 2 oxide, iron 3 oxide. That is rust. Good job. All right, so in addition to that, I want to show you guys a chemical reaction taking place right now. So let me go ahead and get my safety goggles on, get my glasses on, just for safety, right? All right. So right now, I have got 2 beakers of different things right here. I've got some potassium iodide, and I've got some lead 2 nitrate. So if you were to describe this right here, what would you say it looks like?
water.
It looks like water. And if I wanted to test that it wasn't water, how would I do that? No. Don't drink it. Don't drink it. How else could I test that this isn't water for sure? The pH. Okay, I could check the pH. I could mix this with a couple other things, right? I can waft just to see what it is, all right? I can check if it is conductive, right? And if it's conductive, that would definitely confirm to me that this is an ionic compound. If I couldn't do that, how else could I tell that this is an ionic compound?
The label.
What about the label? What's so important about K and I?
They're elements.
Thank you. It's a metal and a non-metal. So what I actually want you to do real quick is I want you guys to stay in your groups, and I want you to grab a whiteboard, and I want you to try to draw a particulate diagram of what you think is occurring on the molecular level, right? You know that we have Ki dissolved in water, right? So what would that look like if you drew a diagram? That's what I want to see. So one person from each group, come grab a whiteboard, a marker, and some paper towels. So once again, I want you guys to try to draw me a particulate diagram of what Ki and PbNO3 looks like on the molecular level. So aqueous means what? Dissolved in water. So if I had Ki in water, would it still look like that? Or would it break
interact
apart?
with the H2O? Or would it dissolve? Would the bonds break?
There we go. So it's going to break those bonds, and then, yeah, water's going to surround it. But let's go ahead and see that broken up.
So I make more?
Make more, add some water.
Do we put the K and the I together?
Well, if it is an aqueous solution like that is, would it stay together in water? No, it's going to be broken apart, right?
Okay, so it doesn't matter, like, I can just...
Yeah, if that's what you want to do. So make yourself a key, that way I know what's going on. This is different. Let's see if we can change it up. Right now, they're not mixed together, so it kind of looks like they're in the same beaker to me. Let's have two separate parts. Let's have this half be a particle diagram and that bottom part be a particle diagram. Okay? And remember, it is aqueous, right?
Yeah.
So aqueous means what? Dissolved in water. Let's see what we have here. We've got X's and O's, X's and stars and all that good stuff right here. All right? So if you were to look at this diagram, tell me what's going on here. If you two were to look at this, what would you say?
That the K and the I have dissolved in the water.
That the K and the I have dissolved in the water. Great. What about this one down here?
The same thing with the P.
The same thing. All right, so I asked a lot of you to draw the water molecules in there, but you don't have to. As long as you've broken it apart, and I know it's aqueous, the point comes across. So good job. That's exactly what I want to see. All right, so let's actually go ahead and perform this experiment real quick. All right, so let's see what happens. I hope it doesn't blow up. That's not going to be good. Foam. And, oh!
It changed color.
This is mustard. Just kidding, this is not mustard. Don't eat this. This is a pretty color? That's a good question. It is kind of thick. In fact,
Is it hot?
how about you fill it?
No, it's the same.
But it is like,
It looks like
it's
sand.
like slimy.
Okay, it is kind of slimy. So if you were to look at the bottom, what do we see going on there?
It's kind of clumping up.
Kind of clumping up. So all of a sudden, we've made a solid. So this is a solid down here, if I were to turn that around like that, right? Is that actually what you expected? Now, if I gave this time to just settle out, it would end up looking like this. So this one happened last night. So I did this one last night, and we have this solution up here, and we have this solid down here. Okay? That's a nice turn of events. So after time, this is what's going to happen. So now I want you to do the same thing. So let's erase that, and let's try to figure out what this solid is. Let's show all of these ions interacting in the same container, okay?
You look at the valence electrons and see.
Where's it at?
Yeah, so
Where's that list that shows you?
it's
So
on the back.
potassium nitrate is a potential product, as well as what?
Lead iodide.
Lead iodide. At this point, I want you to take a guess as to which one it can be. Then we'll talk about it.
Plus 2 according to the acid PBI. Well, right now, we don't know what the product is. We don't know.
That's a soft PB.
It stays at the top and bottom, so you'll have like a film of it up here and a film of it down here. Yeah.
Fair enough.
You can just make it simple word.
Plus 1. Let's look at that equation up there. If we uncrisscross,
That's PB2.
PB plus 2 and NO3 has what charge? Minus 1. So just like that.
Okay.
However,
Oh, wait.
that might have a subscript or
Oh,
2.
yeah, I just had that and then I like erased it.
Okay, so you're going to say that this is the solid right here?
Yes.
Yes.
Okay. So that's what we're going to say, that's the solid. Good. So it looks like most of you are finished, and I see some really good diagrams out here. I see some people choosing lead 2 iodide as the product because you're using double replacements, you know what the products could be, and some of you are using potassium nitrate as a product, okay? All alkali metals are soluble. There are no exceptions. So if you said that KNO3 was insoluble, that wouldn't be the case. Let's move on to the next thing. I'm going to take this off. I'm going to write out this entire equation. Plus PB NO3 to aqueous. What could my products be? What should my products be, gang?
It should be potassium nitrate.
So KNO3 and then PBI2. All right, I'll give you a hint. This, in fact, was the solid. Good job. So this is aqueous. All I want you to do is to write the molecular equation between the reactions that are going to occur on this lab mat here. So for example, the first one's going to be between sodium hydroxide and calcium chloride. Write out what you think the products are, and then I want you to check on your pink sheet what is actually soluble and insoluble, and write a net ionic equation from that. Does it make sense? So what are our products going to be?
NaCl is going to be aqueous, and then Ca.
Oh, that's an easy one, isn't it? Okay. Remember, this is a polyatomic ion, so there should be parentheses around OH. Perfect. All right. So let's actually check and see if we do get a precipitate in the very first one. Okay, so we are getting something. Keep going. Oh, yeah.
Keep going?
Yeah.
Tell me when.
That's perfect. I just want everyone to be able to see this for sure. It did get cloudy. What color is that? White. It's okay.
Feeling pretty good. We assume that it's going to be solid.
Ew, that's weird. Because if it's a
Good, good, perfect. Good job. Even used parentheses and everything. All right, so it came out to be a solid. Good job.
what is that?
That's calcium hydroxide. So now you have to write yourself a net ionic equation that relates only to that. So what made that?
Calcium and OH.
Correct. So once you have this equation balanced, then you can write the ionic equation, right? Nothing's happening. Nothing's happening. If we look at the solubility rules, would that make sense?
Yes.
So what were the two products that you could have had? Potassium chloride.
And calcium iodide.
And they're all insoluble, right? Or sorry, soluble. So there you go. So that's exactly what we expected to happen. Nothing.
What's the solubility of it? It is soluble.
Yeah, and then the other one is CaCO2, which is also soluble. So that's why nothing.
Is this one supposed
Correct.
I want to ask you that question again. At this point in your learning, how would you define a chemical reaction? Does it still match up with what you said earlier today?
Yes.
Okay, even though it didn't get hot or didn't get cold, does that mean that that's not a thing in chemical reactions?
There's just different ways to define a chemical reaction.
Okay, so what happened with the second chemical reaction? How would you describe that texture?
It's like jelly and chunky. You know what's in like an ice pack?
Mm-hmm.
That's what it was. That's what it looked like to me. Like if you were to cut open an ice pack,
Uh-huh.
like a slushy,
Like
Gels
gel.
and gel.
Like that fake snow.
Okay, like the fake snow. All right. And then who was disappointed by the last two?
me, nothing happened.
Nothing happened, but
It combined it, but it wasn't like.
did they really combine?
Well, they did, but they like combined. Like, they
It turned into
dissolved.
a mixture.
Okay, it was just a mixture. It was a homogeneous mixture. Nothing came out. Everything was left as ions. That's perfect. So sitting down and reflecting on the lesson, I do believe that my objectives were met. The students stated they understood what we were talking about, and I could even see evidence in their learning from the immediate lab that we did after that. So while there are a couple things that we need to work on, I believe students have a solid foundation in precipitation reactions and the use of solubility rules. In terms of things I would do differently, maybe next time I would emphasize even more to students that, hey, these are all solids that are dissolved in water. Okay, so that makes it an aqueous solution. So after today's lesson, students will now conduct another lab in which they will get the chance to silver plate ornaments that they can take home. So this is another application of double replacement reactions as well as single replacement reactions. I'm Gabriel Gafford, a chemistry teacher in Bossier Parish. Thank you for watching.